només dir-vos que, encara que siguem pocs, crec que hi ha l'audiència necessària, perquè tenim aquí els responsables de sala, els quals ens volem adreçar. L'Eloi ha estat treballant amb nosaltres. Què, vols tancar la porta? No, està bé.
Sí, si hay este ruido, sí.
Después. No, que hay alguien buscando.
Ah.
Vale. Bueno, l'Eloi va començar a treballar amb nosaltres, o a col·laborar, diguéssim, ja fa 2-3 anys, no me'n recordo, 2 anys o així. Ells estan fent dissenys de dispositius, bueno, que posa el títol, per microones, de dispositius acústics per microones, i llavors, a part de dissenyar-los, van tenir la idea de fabricar-los. Llavors van venir a veure el Jaume, no? I a partir d'aquí doncs, hem estat treballant i suposo que ens ensenyaràs una mica els resultats que has tingut i potser ens explicaràs que també ara estàs treballant en una empresa que es dedica a això i que s'ha instal·lat a Barcelona i que, per tant, el que hem fet és molt positiu i ha de continuar. Sí? Doncs vinga, com vulguis.
Bueno, ¿en qué idioma lo hago? Any preference?
English.
Sí, no? Sí, bueno, si vols, faig en anglès. Well, this is the work we've been doing with CNM also from UAB here during these 3 years. And what we do is mainly microwave acoustic resonators. In this case, we'll talk about a special type of waves we use. They're called plate waves on a special platform that has been recently developed called LNOI. It's lithium niobate on insulator. And we will go through these steps now. So this is the brief agenda of the meeting today. So I'll start by reviewing briefly why do we need microwave acoustics and how important they are, because we have a view of that, but it's not so common to see why we need microwave acoustics. We'll overview briefly the resonator types we have. We'll go a little bit on the acoustic wave filter basics so that we understand why we need these resonators and how can we compose filters with them. And then we will dive into the specific topic of the plate waves and the mode we'll be using, the shear horizontal mode. Then we can present our structure. We'll briefly say something about the manufacturing process here at CNM. And then I will present some results on many experiments we have done. Initially, we played with the electrode thickness on our platform to see which was its effect. And then we also went in finding ways of tackling spurious modes we had called transverse modes. And then we could show a final result. We had some manufactured filters the first time we did them. And there are a lot of other applications that can be applied with this platform. Also, some filters that are actually now undergoing processing here at CNM. So many things to cover. So why microwave acoustics is the basic thing. So we are surrounded by a very expensive and scarce resource. It's something we always say, that is the EM spectrum. We use it for everything, for communications, for anything implying wireless. We are using spectrum and it's completely occupied. What do we require now? Society also actually wants more higher channel capacity. So we need less latency, more data being transferred. So we need more bandwidth. This is the trend. So we've seen that from 2G when going to 3G, then 4G came. Now we are on 5G on deployment. We're already developing things for 6G, while the 3GPP is also thinking about what 6G will be. So we need more bandwidth, and this is just an example. Here you have some bands for the 4G spectrum. These are the band 41, for example, is a TDD band. It's one of the widest for 4G, 194 megahertz at 2.5 gig. Then you have band 7, band 1, band 3. So it's small chunks of spectrum being used for mobile communications, but it's mainly in terms of fractional bandwidth. You have 3 to 4% fractional bandwidth spots there. Once we start implementing 5G, there you have bigger bands that are actually way wider in terms of bandwidth. So fractional bandwidth above 12 to 15%. So that's something we need to take into account. For example, you have this Wi-Fi 6Z example. This is super wide band using the UNI 1 to 8 channels. And we need ways to filter this. Why do we need to manage this spectrum? Because we are using it all around us at any moment. For example, we have this brief schematic here. So your smartphone at some point might be communicating with a base station using, for example, band 7. So if it's a FDD band, so frequency division duplexing. So you're going to be sending information to the tower on the band 7TX band. Tower is going to be sending you information through the band 7RX band, and then maybe you have some Wi-Fi router around, actually covering all the 2.4 gig spectrum. So you need devices inside your smartphone that actually tell your front end, okay, just process the frequency content inside this small portion of the spectrum. So we need filters, a lot of them. And most importantly, we need to implement them inside our smartphones, and we all know how small our smartphones are, so they fit in our pocket. And we now will see why this matters. Now, for 5G, we have more than 90 RF filters inside our smartphone. We have many front ends, some of them even replicated for receiver diversity, etc. Many bands or GPS, Wi-Fi, the 4G and 5G things. They have to also work on Asia, Europe, US. You have many filters around. We could think initially, as we have done, the microwave people, okay, let's use electromagnetic resonators. So we can build filters as in every base station. You can use coaxial cavities, the electric resonators, etc. But in terms of the wavelength, at 2 gig, for example, on free space, you have 15 centimeters wavelength. Since filters are mainly done with resonators that actually depend on the wavelength, how do you fit 90 filters that each of them measuring more than 15 centimeters inside a smartphone? That's one of the, so that's the main objective of why do we need this technology. That's way too large. With acoustic wave technology, in this case, I place here BO or SAW that are actually the standards on the market now. Your acoustic wavelength at 2 gig, for example, this is just an example using aluminum nitride on BO resonators, your wavelength is 2 microns. And you keep a very higher Q, very high Q, to Qs above 3000. So you can actually build super miniaturized structures with a really high Q in terms of electrical performance that can actually be implemented inside your smartphone. These are 2 examples. You can take them from an Investors Day presentation by Corvo. These are old front-end modules. So both have an area of 45 millimeters squared. This is a low band one made of SAW filters. These ones here, each of these dies, it's a flip chip die with BO resonators, SAW resonators inside, and the other one, all these gray things here are BO resonators. In each of them, you have 12 filters. Now, these are pretty old. So you see how small things can get and need to get, because you need more than 90 bands being filtered inside your smartphone. So that's why we need acoustic wave technology. Okay, we have an acoustic wavelength. So actually, we're playing with mechanical waves on our material. All this is enabled by piezoelectricity. So we're using piezoelectric materials so that we can convert an RF signal, an electromagnetic signal, into a mechanical wave. We play with it on the mechanical domain, then we transform back to the electromagnetic world, and we can process it further. But we have already done the filtering on the mechanical domain. So before diving into the topic itself, the group I've done the PhD in from UAB. So we work at the interface or the intersection between 3 main fields. So we do network synthesis, microwave engineering, and physical acoustics. At the intersection of these 3 fields, we are developing our techniques. And what we do is actually develop synthesis techniques for acoustic filters. And this is actually something that is already implemented in the industry. There are many partners that actually now are using software tools by this group. The one I'm working now in, Corvo, has a synthesis engine that is being used by device designers for anything, for their day-to-day work. So what do we refer to with synthesis? When we talk about synthesis, is you normally, when we study at school, engineering, electrical engineering, you get circuits like these, and you know mathematical techniques from which you can analyze the circuit and get the response you want. So the response that these elements and their connection implement. What we do is the opposite. So we are able to find which elements and how should they be connected so that they implement the response that I want. So we start at the mathematical level, we define the function we want to implement. In this case, it's a filter function, these are S parameters. So we know a way in which we can find the elements and their connection so that they implement this response. This is traditional thing in purely microwave filters for cavities and stuff. It had never been applied to acoustic technologies, and this is what we are doing here. Okay, now that we more or less know what we're doing, this is the brief review of the main acoustic resonators we have on the market now. The two on the left, BO and SAW, are the standards on the industry now. So these are on all your smartphones. You have BO, the bulk acoustic wave, in which you have a piston mode that is called. It's a wave that is vibrating in this way. And you have two main types of resonators. They come mainly to companies. Corvo is doing the SMR, the solidly mounted resonator. So it's a thin aluminum nitride or scandium aluminum nitride layer mounted on top of a Bragg reflector made of low and high acoustic impedance layers, so that you have actually a resonance inside the piezoelectric material, or the F-bar. This is Corvo's competitor. They release a cavity underneath the resonator, so that actually they get isolated from the substrate with air. In terms of acoustic or mechanical waves, air is the short circuit, so actually have the best reflectance there. These are two different approaches that are now in the market. So surface acoustic waves, in this case, they use Rayleigh waves on thick layers. In this case, it's normally a wafer, mainly on lithium niobate and lithium tantalate. These are the traditional materials. This was developed initially at really low frequencies for IF filters, and then it got scaled up to the 2 gigahertz range. It's considered that the barrier between BO and SAW is actually at the 2.2, 2.3 gigahertz range. So they are complementary technologies. Normally you have all your low bands from 700 megahertz up to 1.5 gigahertz are SAW filters. Above that, you have BO filters mainly. Just because there's a lithographical barrier here. On SAW, you need to define IDTs. So your finger is actually fixing your frequency. If you go well above 3 gigahertz, the cost of lithography tools is way above what the market is willing to pay, so it's not cost effective. It doesn't mean that it doesn't work. It's just the companies are not going there. BO is way cheaper at those frequencies, and in terms of performance, it's also way above that. What's now coming into the academy and also into the market somehow is what we call plate waves. So this was developed, or was theoretically developed a lot of years ago, but now thanks to the SmartCut technique and the ability to transfer layers, because lithium niobate cannot be deposited, can only be grown on ingots and then transferred. You can use lamb or shear horizontal waves on thin layers of these materials, and that actually they allow you to get really an interesting performance. And this is what we are doing today here. In this case, this is also a type of wave that is going to be excited by IDTs. So we need to define an interdigital transducer on our device. Regarding plate waves, you have mainly two types of resonators. You have a membrane approach, in which below your thin layer of piezoelectric material, you have air. So you can get isolated from the substrate. Or what we're going to do, it's called the LNOI or LTOI, depending if you use lithium niobate or lithium tantalate, on insulator. So it's your piezoelectric material put on top of an isolating layer that has some specific mechanical characteristics, so that it isolates the wave from the substrate. Wait, now we know something about the main types of resonators. So I'll dive a little bit into how we do filters with acoustic resonators. Independent of the type of resonator, any acoustic wave resonator can actually be modeled electrically. So if you abstract yourself from the mechanical domain and you just see it as a box that you evaluate from the electrical standpoint, can be modeled with the so-called Butterworth Van Dyke model that we have here. So each crystal, this is the traditional symbol for a crystal. You have these elements here. So you have what we call a motional branch, CA and LA, that actually model the mechanical resonance. And then you have a parallel capacitor, C0, or also sometimes you see C stat, the sum of CA and C0, that actually models the out-of-band nature of your structures. You have an IDT away in frequency from the resonance. You actually see a capacitor. It's like a lines having an interdigital capacitor there. Or in a BO resonator, you have two parallel plates, two parallel electrodes, so you have a capacitor there. So this is the electrical model of the acoustic wave resonator. From the electrical performance point of view, obviously you will have two resonances. As you can see here, this is the impedance in dBs. So you have a series resonance, so a place or a frequency at which the resonator places a zero impedance. So you have a short circuit through it. It's when the motion alarm resonates. And then you have the combination between both. Above the resonance frequency, the motion alarm turns into has an inductive behavior. So then you have an L here with a C, the C not in parallel. So you have an open circuit. At some frequency above Fs, you have Fp, that is the anti-resonance frequency, raising an open circuit. And relating these two, there's a key figure that is really important and has a lot to do with the mechanical domain that is called the electromechanical coupling coefficient. It is physically a measure of how efficient your material is at transducing electrical energy into mechanical energy. But in the end, it is also related to how these two resonances are spread apart. So the relative distance between Fs and Fp is going to be defined by the electromechanical coupling coefficient. And this is going to be really important when we want to design filters. And it's going to be really related to the bandwidth, as we have said at the beginning. So how do we compose filters with the acoustic wave resonators? The basic topology, it has been used for many years now. It's the so-called ladder topology. See that this is a filter that is composed of electrically connected acoustic wave resonators. So each resonator is actually performing an electrical response in terms of resonances, but waves go into the mechanical domain, resonate there, then go back, but the connection between resonators is electrical, okay? This is actually an interesting fact because you're not coupling things on the mechanical domain as we would be doing on electromagnetic filters like cavities, but we connect them directly together. How do we compose a filter with a ladder filter? So if we have series resonators, you can see that, okay, when this resonator here, resonates at its Fs, it's going to place a through. So you have signal going through the main line of the filter. So you are actually, okay, you're not going to affect the signal there. But at its Fp, you're going to place an open circuit. So this series resonator is going to place transmission zeros here above the passband. You can see here, this is the plot of the red line and the green line. You can see that they actually place their Fs inside the passband and their Fp outside the passband. With shunt resonators, it is the opposite. So when this shunt resonator resonates at Fs, you're going to have signal flowing to ground. So you're actually placing a transmission zero below the passband. So with a shunt resonator, you place Fs outside the passband and then you place Fp inside the passband. Okay, this is the main idea behind ladder filters. They have specificities. For example, they implement what we call fully canonical functions. So the out-of-band rejection is finite. You don't have the typical electromagnetic filter shape in which you have decaying slopes. And see that there's a key fact here. So that the achievable bandwidth on the filter has a lot to do with the electromechanical coupling of the resonators. In this case, this filter is composed by 3 resonators, all of them having a 6.7 electromechanical coupling coefficient. And you can implement actually passbands that are more or less have a fractional bandwidth that is more or less the half of that electromechanical coupling coefficient. That is a rule that has been on the industry and we have played with it all around and it's consistent. So what was happening with 4G? You had bands that were like 3-4% wide in terms of fractional bandwidth. So with these basic technologies, aluminum nitride, BO, or lithium tantalate SAW, you had these couplings here. These were the achievable couplings. You could build those filters with those technologies easily. But we have already seen the 5G bands we have now, N77, M79, the Wi-Fi 6Z, that those are way above this. So we cannot implement those filters with this. How do we increase KT squared? That's the main goal of the industry, has been that for many years. We cannot do these wideband filters with aluminum nitride and lithium tantalate. So there are 2 main approaches here. For BO, they went for the scandium doping of ALN. This was proposed by Akiyama many years ago in 2009. And they showed that actually by doping your aluminum nitride, you could go up in coupling a lot. increasing a little bit viscous losses, but in the end, this is now on standard in the industry. So even from really low values of doping with scandium to really high values, you can play with the coupling around. And on the other side, there's what was proposed by Kuznetsova many years ago, just from a theoretical standpoint, because this was not actually manufacturable at the time. It's using plate modes with thin films of both lithium niobate and lithium tantalate. This was originally just studied as a mathematical or theoretical study because there was no way in which you can get thin films of these materials with a correct crystalline orientation. With SmartCut technologies, now Soitec is selling a lot of lithium tantalate wafers, thin films of them. You can get really thin layers of lithium niobate and lithium tantalate on wafers mounted on top of a thin silicon oxide layer. So you can actually start playing with these modes. And there have been a lot of demonstrations using these modes, especially, for example, there was a company called Resonant that demonstrated what they call the XBAW. It was a thin layer of lithium niobate providing a coupling above 30%. That was a kind of revolution. They are running into other problems, but they started demonstrating these structures. What we're going to do is we're going to build resonators using this same approach, the plate wave resonator with a type of thin lithium niobate film. Okay, so what Kuznetsova predicted in 2001 was that you could achieve like 35% coupling with a phase velocity of 4,500 on Y-cut lithium niobate layer. It should be pretty thin, so H over lambda is 0.1. But and he proposed using the SH0 mode, the shear horizontal mode. We'll now see what these modes mean. But he only explored the three main cuts, so Y-cut, X-cut, and Z-cut. So the Y-cut, for example, pointing outwards from the wafer, and then explode, changing the propagation direction. Actually, it has been demonstrated that we will show now that if you tilt the axis further, so you don't restrict yourself to being on the cut plane, you can get even further than this, and which this is what we're going to be using. So on a thin plate, this is just mechanical. So this is not a piezoelectric plate. In any plate, you can get three main modes. There are other modes that are combinations of those, but mainly the two lamb waves, the asymmetric and these symmetric waves, and then the shear horizontal waves. These have been also called love waves if you have an interface between a low velocity material and a high velocity material. But this is a wave in which the material vibrates in this direction and the wave propagates in that direction. I think should be this nice picture here. Allows you to see how the material will start vibrating. This is in contrast to what we call the SAW wave or the Rayleigh wave, in which it's just completely surface wave, in which actually the particles in the material describe an ellipse. So this is just a Rayleigh wave can only exist when the substrate material is really thick. If you go to thin layers, Rayleigh wave cannot exist, and you only get these plate modes. So we're going to choose the shear horizontal mode as Kuznetsova predicted because it offered a really wide coupling, high coupling. And we started doing some FEM simulation that was performed by Jordi Verdú here, so I took these figures for him. There's one thing you need to account for, as we're playing with piezoelectric materials, so they should be anisotropic. But limbo or LN or lithium niobate, it's a super strong anisotropic. So you have a lot of dependence of your wave properties with respect to the angle of wave propagation. So what we started doing here, this is a rotation angle beta, so it's an angular rotation. So actually we are moving we are on the Y-cut, and we are moving the axis from the wafer. So the Y-cut is not going to be pointing upwards anymore, so it's going to be moving this way. And in any of these cases, we're going to be propagating along X direction. So what we can simulate is actually you get your thin layer, and then you simulate both fixing an open circuit condition on top. So it says you have nothing in there electrically, and then a short circuit condition, you have two infinitesimal thin metal layers there. You can simulate both the open and the shorted or the short velocities, and from those you can actually compute the achievable coupling. What we see here on the black line is the achievable coupling for the SH0 mode, for an orientation, having a maximum, a really big maximum at 30 degrees rotation from the y-axis. You can see that here there are a lot of other modes, because all of them can exist on your plate. So actually you have your asymmetric and symmetric modes and their higher order harmonics. So you have S1, A1, SH01, and you have the coupling of all of them here. What is really good here is that you actually, when you have a lot of coupling to your SH0 mode, you have super weak coupling to the rest of modes, excepting the symmetric mode. We will see that the symmetric mode is actually popping up as a spurious in our measurements, but it's really contained because we will see something now on the next slide. Okay, now we know the cut we're going to play with because you get the maximum coupling from here. There's another thing to revisit. Interestingly, and more importantly, the SH0 mode shows no dispersion with the plate thickness. So you can sweep here for the thickness of the plate with respect to lambda. And what you can see is that actually your phase velocity is not changing. This is a really important aspect because it allows you to choose which is the region in terms of h over lambda ratio that you're going to be working with. And we want to stay in this area below the 25% ratio because the phase velocity of all other modes are well away from our phase velocity. That means that our structure, when we define the IDT, is going to be efficiently exciting the SH0 mode. It's not going to be anywhere or close to defining any lambda half or lambda quarter structure for any of the other modes. So you have no excitation to the A0 mode, no excitation to the S0 mode, because their velocities are way above, one is below and one is above. What is also good about this mode showing no dispersion is that we don't really, well, we will be worrying about the thickness of our layer, but since SmartCut technologies can assure you, you can buy a layer of 500 nanometers thickness, but then you will have some roughness and then some plus minus discrepancy. It doesn't really affect you if your layer is like 40 or 20 microns away or below your desired thickness. So the frequency at which we start playing or building resonator is not going to be affected by small deviations on the thickness. So the same structure with the same pitch that we define for the RDT is going to be working precisely if we have this kind of differences in terms of the layer thickness. So this is a pretty interesting characteristic of this mode. So this is our platform and what we have been developing. Initially, we started working at this. Our aim was to work at 1.5 gigahertz just to have something that was manageable, that was lithographically not at the extreme of anything, so that we could focus on the mechanical properties of this. So if we assume, for example, a phase velocity of 5,000 meters per second, that is the ideal value we can get to. So you have an electrode width, because electrodes will be quarter wavelength wide, around 500 nanometers. This is something that we can define, I won't say easily, but it's not at the extreme of lithography tools. So we call it the LNOI because we have lithium on insulator. So we have this yellow thing here is our lithium niobate layer. Then we have a thin silicon oxide layer that is actually behaving as an impedance inverter for the waves that might actually be propagating towards the silicon. So it's isolating our layer from the substrate. Because when we are exciting the shear horizontal mode on the plate, we might actually also be triggering shear waves that are actually traveling vertically down towards the silicon. That's going to be energy leaking from your resonator outside of the resonator, so it's going to be energy that is being lost. Your Q goes down. With this layer, we are actually isolating the substrate from our thin plate. So this is actually something pretty important. We bought this wafer specifically with these measurements, with these thicknesses, so that we could work at this frequency. Actually, the thickness of this layer it depends on the shear velocity of the phase velocity of the shear waves on silicon oxide. We took this from a NIST standard. So considering this frequency, you have that this 600 nanometer silicon oxide layer will work as a impedance inverter at around 1.5 gigahertz. Okay, so our resonator is going to be this IDT here, and we have to define at both sides of the resonator what we call the grating reflectors, because we need a way in which we can confine these shear horizontal waves inside the resonator. If we don't confine them, they're going to be propagating through the material, but they're going to be lost. We need to make them bounce back so they build a resonance, and then we have this resonator constructor. Okay, what parameters are now remaining to be fixed? We have to think about the thickness of the aluminum electrodes. This is something important we will see now. The number of fingers per grating and the duty factor. Duty factor is the ITT duty factor, so it's the ratio between the electrode thickness and the space of the unmetallized region. Without diving into the discussions that led to choosing these values, for example, in this case, we're going to be using 40 fingers per grating because we did an initial experiment using 20. We saw that there was no enough reflectivity, so with 40 we're okay. And with the duty factor, we did the same experiment, and we know that for a 40% ratio between metallized and non-metallized region, we are at the position in which we have the better coupling. And we avoid exciting other modes because there are other dependencies with the duty factor that we don't have here in this presentation. So just to review briefly from the process side. So this is the simplest approach. The LNOI is the simplest approach because since we can actually purchase the wafer from manufacturers, the main manufacturer now is Soitec. It's providing wafers to the industry, but for academic purposes, NanoLN and NGK are actually providing these wafers, both for lithium niobate and lithium tantalate. So what they do is this SmartCut layer transfer. And this is the structure we're going to be defining. So you have a grating on the top, then you have the central body of the reflector with another grating, and then the boost bars. So actually, since we have a 500 nanometer, more or less, electrode width, we're going to be resorting to electron beam lithography, because this could also be done with a stepper, but we went for the electron beam lithography. And it also provides you a higher degree of flexibility because you can actually play with your design, rerun and change things. The only problem we might run into that actually Albert and Chevy solved is that you have long structures here. You have to really long fingers, really tight spaces. You need to take that into account, but that could be done. So in the end, from a process standpoint, you only need to deposit aluminum, then lift off, and you have resonators. We have two processes initially because we have this landing patch for our probes. We are doing that with laser lithography easily, and then we go for the electron beam lithography for the resonator body itself. So what we did initially is try and experiment with the thickness of the electrodes. And we manufactured a set of resonators. We swept around lambda, so in 100 nanometer steps to get a range of frequencies around the working frequency. And we went for 81 IDT fingers. This is a normal measure to have a normal sized resonator providing like around 0.5 picofarads of capacitance, which should be enough. Number of grating fingers 40 and duty factor 0.4. And then we build the same structure using two different aluminum thicknesses, 120 nanometers and 180 nanometers. This is an important measure in terms of what the thickness of the electrode to the lambda ratio, 3.5% and 6.5% in this case. There are studies that have shown that you have an optimal, as we will see, at around 6 to 10%. There are many studies around this, but they vary in terms of which aluminum they are using, which is the process they are doing. So we don't dive into that. What we're going to see is that, okay, we measured the 120 nanometers resonators, and we obtained these measurements here. We see the FS and FP of each resonator, but the important thing that we saw is that there's energy being coupled into spurious modes above FP. So you can see here there's a hump in any of the resonators just above FP. So that means that actually your resonator is being, your waves or your IDT is actually putting energy into waves propagating at those frequencies that are not useful for a resonator. They are sucking away Q and coupling. So we need to handle that. These modes, Jordi did some simulations, and they are mainly due to longitudinal waves that actually propagate through the two gratings. So we went for the 180 nanometers electrode, and we saw the following result. The fact is that when you grow up in electrode thickness, you're actually adding a higher mechanical load on your resonator, so you're actually moving your phase velocity slightly downwards. But the distance between the gratings and the modes propagating between the gratings do not change from their frequency at which they propagate. And now, since our resonator has moved slightly downwards, the energy that was being trapped inside those longitudinal modes is now inside the stop band bandwidth, or the reflectance bandwidth of the grating we have. So actually you can see here the measurement that we have low amount of energy or low coupling to the spurious mode above FP. And clearly you can see if you compare like two similar resonators from the top plot and the bottom plot, we have a better QP and they are slightly wider in terms of coupling. Here's just a cross SEM, was a feed cut that Chevy did just to make sure that we have the thickness, and you have 180 nanometers metal, then you have 140 nanometers lithium niobate, and then you have 600 nanometers of silicon oxide. So this is our LNOI structure. So we have achieved a pretty interesting resonator. So maybe it doesn't seem like the best resonator, but in terms, if you consider that we're playing with mechanical waves on a thin substrate that has to be excited with IDTs, this was for us an amazing result. And we analyzed these three best resonators. These are the ones that are closest to the working frequency of our structure, so the closest to the 1.5 gigahertz at which the silicon oxide layer was providing this isolation from the substrate. And here we have some data from these resonators. Actually, we measured both the Q of each resonator, so we had an interesting Q max of around 600, 650. An impedance ratio, so it's the ratio between the maximum and the minimum impedance. So your impedance at the FS and your impedance at FP from 60 dBs. That is really interesting. In order to build filters, you want the maximum impedance ratio you can have. And we are obtaining a KT squared of 14%. See the initial figure, we said that aluminum nitride Bohr resonators provided a 6.7% coupling. You couldn't go away above that because of ALN and its C33 parameter. And lithium tantalate SAW was providing 8.5, and that was it. So now we are going well above that. See that we are actually way below the ideal achievable coupling that Kuznetsov have predicted, because that was an initial study. They didn't take into account the thickness of the electrodes and the mechanical loading they provide. And there are many variables here, actually. The fact that we have a layer transferred on the silicon oxide, you have interfaces with different crystallinity, etc. So you have things that are adding differences on top of your mode, but actually you have gone way above the expected or the limits and coupling that we had with other technologies. We have two main concerns here, is that you can actually see that in between the two resonances, we still have these small ripples. These are transverse modes. So these are waves that are actually not propagating. If I go here, they are not propagating in this direction. So where the wave should be propagating along the IDT, they are waves that are actually propagating in oblique directions. This is why they are called transverse modes. And because they are being trapped between the two bus bars, and we'll see now how to tackle them. Another concern we have is electrode resistance. We are using aluminum nitride here. In this case, you can see here at the FS value in terms of impedance, we have 18 dB impedance there, input impedance. So that means we have an RS of 8 ohms around. So that's something we want to focus in, improving the Q of the series resonance. You can see it should be for the central resonator, it's around 200, that frequency. So this is something we can really improve, because actually we expect that we are losing at around 7 and 6, 9 dBs of impedance ratio just because having a too high resistivity on this electrodes. Okay, so we're gonna focus on the transverse modes that we want to play with. We want to get rid of them. What we went for is what's called the apodization of the IDT. This is something that had been traditionally done in SAW resonators because they are really prone to exciting waves in many directions. There are many studies and many papers regarding apodization of IDTs and how to handle and confine the wave perfectly at the center of the IDT and not allowing it to propagate obliquely. And we thought on applying these apodization patterns to our IDTs, and then we studied both the rhomboidal and elliptical patterns, just to have two different shapes. The rhomboidal one is the most traditional one in SAW technology. If you get your eyes in any SAW chip, you'll see some kind of rhomboidal pattern on the IDTs. And here we just have two pictures of the two patterns we have. In this case, see that we are using, so at the center we have the maximum overlap between IDTs, the IDT fingers, and at the extremes you have no overlap. So this is what we call the apodization ratio. In this case would be 100%. If you have a 0% apodization, you have no shape. You have both cut lines facing each other at each of the sides of the resonator. Here we just have an SEM image of one of our apodized resonators. So you can see that we had to cut a little bit the finger at this position so that the active area of the resonator actually defines this rhomboidal shape. Okay, so what we did is we'll go through both the rhomboidal and elliptical, but we get the 1450 nanometer resonator, and we have a sweep from 40% to 100% apodization ratio. And you can see actually, just by comparing it with the previous measurement, that you have no modes in between the two resonances. We cannot really see it now, but we will see that we have improved a lot in more electrical performance parameters. But we want to focus into this, and you can see that actually both or all resonators for any apodization ratio seem clean in terms of impedance, but we like to see it on the face of the impedance. If you look at the face of the input impedance of the resonator, you can actually see any mode that is actually sucking energy out of your main mode, because you're going to see phase going in opposite directions to the one you expect. The resonator should be out of band. It's a capacitance, so you have a minus 90 degrees, you should have. And in between the resonances, you have an inductive behavior, so you should see a plus 90 degree phase. So we can see here for a 40% apodization, okay, we have cleaned the modes in terms of the impedance curve. We don't see them, but if you look at the phase, we still have some ripples here. If we go up in apodization, we see that we get cleaner and cleaner, but notice that we somehow are starting to lose a little bit of coupling. So while FS remains almost unchanged, your FP is actually moving just by changing the apodization ratio. This is something we don't really want because we were aiming for coupling. So we want to clean the spurs, but get the maximum coupling. Actually, you can also see that you might even get stronger modes above FP. So this is something in which we need to find an optimum. And the optimum, in the end, it's at the 60% apodization. This actually confirmed some results we had seen in some old papers by Japanese guys that were doing SAW. So they always proposed the 60%. So now we know why. This is the rhomboidal apodization. If we go to the elliptical apodization, we see a somehow similar results. So we see that we have cleaned in terms of impedance. You can see that there are no ripples in the middle as we saw before. But see that the cleanliness of the resonator is not as good as the one before. So the fact that you have now an elliptical shape, so it grows, the apodization grows really fast from the point at which you started doing it. And then you have a really big zone in the middle that is actually completely parallel, so in which you have no effective apodization. You end up not cleaning the modes completely. And you can see this on the phase curves here. So you have still some in-band ripple on the phase. You might not be seeing it in terms of impedance in dBs on the left plot, but on the right plot you see it. And this actually means that your resonator is actually putting a little bit of energy there. So your resonator, when it is part of a filter, it's going to be having a little bit of bumps inside. So it's something we don't want. So the elliptical apodization was a nice study and a nice way of playing with the resonator, but we decided to go for the full rhomboidal apodization. And this brought us, well, okay. We saw that the more you go up in apodization, you could actually start losing coupling. So we didn't want that. But in terms of Q, just by the fact that you are actually confining your mode better and you don't have energy going inside your spurious modes, see how the Q grows just by increasing the apodization ratio. So as I said before, we have an optimum in this case. We want the Q to go up, but for example, the highest Q, you get it for 100% apodization, but we saw in the previous slide that we had less coupling there and that you could actually end up coupling a little bit more energy into the modes above FP. So we want to find this 60% optimum. This is what we have selected, but see the huge jump in Q that we have done. On the previous resonator, we had 600 Q. Now we have something above 800. So it's just by introducing a shape on the IDT, we just went 200 value up in Q. Obviously, here you can see this is the elliptical Q. So the Q for the elliptically apodized resonators, you can see that the increase is not so high. You get rid of part of the modes and design modes you had, but you cannot really confine them perfectly. So you don't go as high as we would like. So that's why another reason for us to stay with rhomboidal apodization. It was the main outcome here. Here you can see it better. So these are the two best resonators we had on the previous run. We had no apodizations. This is what, so we had an IDT like this one here. So thanks to the thickness of the electrode, we reduced the spurious modes above the anti-resonance of the resonator, but then we had the in-band transverse modes. Thanks to this 60% apodization, so we have an IDT like this one here, we have an almost completely clean resonator in which just by seeing it, okay, RS is going to be the same because we have the same aluminum. So we have the same value here, but see how high we have gone in terms of Q or of impedance at FP, just by comparing them on the table. So we have jumped in Q at around the value of 200 and in coupling too. We are confining the mode better. We are more efficient at transducing energy from the IDT into the SI0 mode. We are not losing energy into the transverse modes. So actually we had a 14% KT squared, we have a 70% KT squared. So this is a really high value if you compare it to the ones we saw at the beginning. Okay, we had a resonator. We were really happy with the result we had. It was a super good resonator for us. And we said, okay, so now we have a clean resonator, so let's start playing with what we know how to do, is that the designing filters. So with our synthesis techniques, we can actually easily get to the, compute which frequencies and which capacitances we need to get a desired response. And we did two cases. These were on the same die in which we did the apodization test. And we did two filters, two basic filters at the beginning, just to test our resonator. So we built a third order ladder in this case, applying some knowledge we have on synthesis, playing with the reflection phase of the filters function we want to implement. You can actually get rid of the input and output inductors that are actually common in acoustic wave filters because they are needed for a phase matching role. So we build this filter here. It's a shunt, series shunt, so third order. And then we tested something that was kind of a crazy experiment, but it's something we ended up finding while working on synthesis, is that if you really take care of the phase of the filter function you want to implement, you can actually go and break the rules of the ladder that I just explained. I told you that series resonators place zeros above the passband, shunt resonators place them below, and that's it. That made sense. So we found out how to play with that through the synthesis, and actually we ended up building a filter that is actually has this structure. So you have two shunt resonators and one series resonator, but has only one zero below the passband and two of them above the passband. Okay, so we had these two structures, and just showing here the die we manufactured. Here we had the apodization study with it, and here below we have the filters, so they are tiny. This is just to show why we need these filters on our mobile phones. Not in this case with this technology, but SAW and BAW filters, because there's nothing that can compete against the miniaturization you can get with acoustic waves for now. So we measured the third order ladder filter with it, since it needed no inductors because we had taken care of the phase. We could actually measure it on die In here, I should say that we have an impedance transformation because this was an error of mine. I'll explain that afterwards. So the filters were matched to 25 ohms instead of 50. That was on my own. But we have this filter here. So this is a third order filter in which we have this nice passband here between, it has 90 megahertz bandwidth. This is a wideband response for the filter. And actually, if we take a look at the reflection phase of the filter, this is something we wanted to control, and we know how to do it from the synthesis point of view. So we knew that we were not going to need any input or output inductors if we were keeping this horizontal asymptote of the phase exactly at this value. So we measured it and it was there. And then here we have an insertion loss close-up of this filter in this case. So it's pretty flat. The reason we have a 2 dB insertion loss at the center of the passband is mainly due to the RS of the resonators. So actually, since we have this topology here, so all the signal that goes through the filter is going to go through this resonator that has actually an 8 ohm series resistance. So you're going to lose a lot of energy there. So that is the main contributor to the insertion loss of the filter. But it's actually a nice result for us. Okay, so this was we were super happy with this. Then we tested the other one. We went for the breaking the ladder thing, we called it. So here we have a filter that is actually having 2 shunt resonators, 1 series resonator, but you can see clearly that you have 1 0 below the passband while having 2 transmission zeros above the passband. This was kind of a crazy thing that we're now writing a paper about. Here, the good thing is that, okay, if you think about keeping your resonance that actually places the transmission zero outside the passband, even below or above, and the other resonance inside the passband, what you would need to do this is a resonator that is actually not acoustical, because you need that the C0 in parallel to the motional branch be an inductor. We are not doing that because we have an acoustic wave resonator. What we actually have is a filter that is composed with a resonator that actually places its Fs here and its Fp is around here. But we do it in a way controlling because synthesis allows us to do that, because it tells us, okay, put this resonator with this impedance there, and it's going to actually be doing what you want it to do. So here we have the response close up and the out of band response. Due to the fact that we are playing with these type of structures, we get a super high out of band rejection here for higher frequencies. We have some loss here that we need to study, because this is, I don't know if it's like waves, mechanical waves that are actually leaking out of the resonator at this frequency, or maybe some radiation we need to study that. And if we look at the phase, this is exactly what we wanted to see. So we needed to have this type of reflection phase both in S11 and S22, so that we could do this change of position of the transmission zeros. And if we look at the insertion loss close-up, we see this here. Why the other one was so flat while we have this one with this ripple in the middle of the passband? It is mainly, if you recall these modes here, we still have a little bit of ripple above SP, because we have suppressed the amount of energy going into those modes, but they still exist. So we can further improve how we avoid those spurs there, because actually your series resonator is placing your shunt resonator is placing its FP at the middle of the passband, and those modes actually in the middle of the passband. So that's why you see here this ripple. This is okay for us. This is something to avoid if you want to construct the filter from a commercial point of view. Okay, when we saw this is the point at which we stopped initially. So then now I'm writing the PhD. I'm working for this company. But what we saw is that, okay, we found out how to play with the thickness of the electrode in which we can, in a way, so to avoid spurious modes above FP, we found the best apodization ratio to avoid the transverse modes, and then we saw that we were increasing in coupling and in Q. We have very promising values now, so that we have a resonator that we know we can trust, and we can actually start building more complicated structures to test other synthesis approaches. And it is not only in terms of filters that we want to test it. this resonator can have many more applications. We now know how to get this value of coupling and how to confine it into a resonance, then you can do many things. For example, one thing I've seen people working with this kind of resonators, with acoustic resonators, is for sensors. For example, you have a microfluidic channel on it, and you have something that actually traps what you want to sense. On the resonator, you're actually adding some mass to the resonator. So you know mass is actually adding mechanical loading to the resonator. So your FP, your phase velocity, VP goes down, and your K goes also down. So you can actually build a sensor in that way. There are commercial applications for that. Now there's ongoing interest. I think the people at Kilimanjaro are interested in developing parcel filters for their qubits using these structures to increase the coherence time of their qubits. We want to scale up in frequency because we were starting this exploration at 1.5 gig. We want to go up to higher frequencies, even going to the FR2 range of 5G at 24 gig. We don't know. At some point we'll get there. And then these are just two examples of filters that are actually being on the actual run now on CNM. So there's a dual band example that UNIS did, and what we call the H ladder. This is a specific thing that we will have many things to say about, but these are just more things that are now being built now that we have this resonator and we know how to control it. Just as a further research topic, there's something that CNM has also been working in, is that maybe we can also try with our wafer going into the released membrane approach, because then your Q goes way up, because although we have this simple λ/4 layer of silicon oxide isolating from the substrate, so it is narrow band and it provides a limited amount of reflectivity and a limited amount of confinement from the silicon substrate. If you put air there, you have perfect confinement, so your Q, all your energy gets trapped inside the plate. However, the main challenge here is etching through the lithium niobate, because that's known to be one of the most challenging things to do for people working in this. The people who have tried commercial applications using this, they are now doing backside etching on the silicon because they don't really want to go into the etching of lithium niobate because a lot of byproducts and things. But I think Roger was trying something in this way, so this is an ongoing study also. Many things that can be tested on this platform. And that should be all on my side.